We have talked about several techniques for solving differential equations, but as I've mentioned before, there are many differential equations that cannot be solved. We cannot find an algebraic formula for the solution. So the question that we need to ask is, how can we find an approximate solution to the differential equation when we cannot find an exact solution? You may be wondering, in fact, how is it that slopes is able to generate a solution when you tap on the graph? To figure this out, we should look back to one of our observations that the solution to the differential equation seems to follow the trajectory of the slopes. That is because the slope field is giving the slope of the tangent line to the solution at every point y and t. So the solution follows the slopes. So we could ask the question, can we come up with an approximate solution to the differential equation by just following the slopes? So let's look at an activity that will allow us to just follow the slopes to the differential equation. So we're going to look at the differential equation y prime equals ay plus b, where a is negative 0.5 and b is 2.5. And what I want to do is start at the point y of 0 equals 1 and follow the slopes. So here I've put an arrow on the screen, and that arrow is going to change its trajectory based on the slopes in the slope field. So I'm going to attach this arrow to my initial point y of 0 equals 1. And what I'm going to do is follow that arrow for a time step of 1. And this is going to be my approximation to what y of 1 would be. In this case, I know that y of 0 is 1, and if I follow that slope, then y of 1 is approximately 3. Well, once I've gotten an approximation for y of 1, I can then grab another arrow that's going to follow for another time step, and I can follow the slope at the end of my first approximation. And now again, I can get another arrow and I can move that one into place, and I can follow the slope that's at the end of my previous approximation. So that at each time step, I'm going to reevaluate the slope at the end of my approximation and then follow that slope for a small amount of time. And piece by piece, I can then build an approximation of the solution. And you'll notice that this approximation appears to follow the slopes. So it looks a lot like the curves that I showed you that are solutions to the differential equation at the beginning of this video. So let's try to formalize how this type of method would work. So here's the problem that we're given. Suppose that you're given the derivative of a function, dy dt equals f of ty, and the value of y of t at some initial point t sub 0. We're going to call that initial value y sub 0, which is y of t sub 0. And the question is, how can we estimate the value of y at other points? The method that we want to use is we want to follow the slopes. Well, these slopes are the slopes of the tangent line to the solution. So I'm going to write down the tangent line approximation to my solution, y prime equals f of ty. Okay, so y is going to be approximately y of t0 plus the derivative of y at t0 times t minus t0. That is the approximation, the tangent line approximation of y centered at t0. Okay, so now I want to figure out specifically, like, what is y at a specific point? We'll call that point t1. So then I'm going to call that, let's see, y of t0. And then I'm going to add the derivative at t0, but I actually know what the derivative at t0 is. It's f of t0 y0. Okay, because I'm given the differential equation, and that differential equation tells me what the derivative is. Okay, so this is evaluating the derivative at that initial point. Okay, and so then I'll multiply that by t1 minus t0, which is the distance in time from the initial point t0 to the point I want to approximate at t1. And so this is going to be my first approximation to the solution of the differential equation at t1. This actually is going to be the beginning of a recursive sequence that will estimate the values of y of t. So now I want to define that recursive sequence. So I'm going to let each time point be the previous time point plus delta t. So in essence, I'm going to say that the distance between two time points is called delta t. And then we're given, of course, the initial time point t0. So what does this sequence look like, where tk plus 1 is tk plus delta t? So I'm going to start at t0, and then t1 is going to be t0 plus delta t. And then t2 is going to be t1 plus delta t. And t3 is going to be t2 plus delta t. And this will go on for a bit until we get to, say, tk, which is tk minus 1 plus delta t, and then tk plus 1, which is tk plus delta t. Importantly, we want to show here that the distance between each point is going to be some distance delta t. So this is a sequence of time values at which I'm going to approximate the solution to the differential equation. Then I'm going to use tangent line approximations to approximate the solution to the differential equation. So I'm going to define a sequence of estimates of y of t, and I'm going to call them yk plus 1. Yk plus 1 is supposed to approximate y of tk plus 1. And I get that by starting at yk, and then I add the derivative at yk, which is f of tk yk. And then I multiply that by the distance between the two time points, which in this case is going to be delta t. So yk plus 1 is going to approximate what we believe the true solution is, which is y of tk plus 1. So what does that sequence look like? Well, I'm going to plot down what my time sequence is. So I'm going to start t0 there, t1, t2, t3, etc. And then I'm going to start at some point, I'll call that y0. And then I'm going to evaluate the slope at that point, and I'm just going to essentially follow the slope. So I'll evaluate what the slope is. In this case, the slope is f of t0, y0. And I'll follow that slope until I get a new point. We'll call that new point y1. So that this point right here is we'll call it T1, Y1. Okay, so now that I've got my first point, y1 is going to be y0 plus the slope evaluated at t0, y0 times delta t. Okay, then at that point, I'm going to reevaluate the slope. And I'm going to follow that slope for another delta t, which will lead me to another estimate y2. And y2 is estimating y of t2. So that point's going to be t2, y2. And then I would reevaluate the slope. And I would follow that slope for another delta t. And that would get me to the next point, say y3. And then I would continue this process of just reevaluating the slope until I get to the last point. This procedure is known as Euler's method. Euler's method is developed by the famous mathematician Euler, and his name is not pronounced Euler. I know a lot of people are familiar with the mathematician Euclid, and so immediately they want to say that it's pronounced the same, that it's Euler, but in fact, the correct pronunciation is Euler. So the question that we could ask once we've got this first approximation is, how can we increase the accuracy of this estimate? So you can see that what I have are straight line segments that are supposed to approximate a curve. So how can I make that more accurate? I can do that by using smaller time intervals, so smaller delta t's. And so if I go back to my estimate here, and you can see that this is my estimation of the solution to the differential equation, instead of using a delta t of 1, or which in this case was 10 segments, if I use 100 segments, which gives me a delta t of 0.1, then I can estimate the solution to the differential equation, and now it looks a little bit more like the curve that I saw when we were first looking at the slope field for this differential equation.